Wire and strings. A current carrying wire of length L and mass M is suspended on two light vertical strings in order to keep the wire horizontal. And that's this picture here. When a uniform magnetic field is established in the same region, the wire is pushed to the right and the strings make an angle theta with the vertical. And that's what we're showing over here. Okay? What is the direction of the magnetic field? And on the below right diagram, where we took this guy here and rotated him into the page, so you see the current going into the page like that, hanging from the support there with the string. Show all the forces acting on the wire. C. Find the magnitude of the magnetic field using the following information, and I give you the current, length, mass, and the angle theta that the wire is displaced by the magnetic field. In another scenario, two parallel wires carrying equal currents in opposite directions repel each other. The length of each wire is 2 meters, the length of the supporting strings is 0.9 meter, the angle from the vertical is 1.5 degrees, and the mass of each wire is 0.050 kilograms. Find the magnitude of the current in each wire. What is the direction of the magnetic field? Use the right-hand rule, which is a handy way, get it, to operate the vector cross product. And right here, this tells you the force, the magnetic force on a current carrying wire in a magnetic field. So this L cross B means that the force will be perpendicular to the direction of the current, right? That's what L is telling you. That's the direction of the current. And it'll also be perpendicular to the magnetic field. So you have three quantities perpendicular to each other. That's the right-hand rule. Now the wire, when it was at rest before the magnetic field was put in, is right there. So there has to be a force to the right to move it to this position here. So you place your four fingers in the direction of the current into the page, your thumb in the direction of the force, which is to the right. Your palm should be facing up, and that's the direction of the magnetic field. So the external magnetic field, again, we're not looking to any magnetic field created by the current. We want the external field, which is making this wire move in that direction. It is directed to the top of the page. So we have the current going into the page, magnetic field up, force to the right, everybody's perpendicular, we're good. On the below diagram, show all the forces acting on the wire. When the AP Physics C exam asks for the forces, it is not necessary to resolve them into their X and Y components. Although you won't lose any points if you do, and frequently you'll need that later on. But this sketch, and I recommend just doing this so you don't confuse the grader, will earn you full credit. You've got gravity pulling it down, magnetic force pushing it to the right, and the tension of the string acting along the string. You will lose credit for extraneous or missing forces. So if you leave one out, you lose a point, and if you were to put in, let's say, I don't know why I do this, but draw another force here for the normal, that doesn't exist. In this case, you would lose a point there. So let me just erase this so again you can see what would get you full credit. Find the magnitude of the magnetic field using the following data. First thing you have to do is resolve the tension force into its X and Y components. And you do a little bit of geometry there, and you find here's T sine theta, here's T cosine theta, and you'll go, wait a minute, shouldn't cosine be on the x-axis? Nope, look at where your angle is. Okay, don't be tricked by that. So let me just erase this here so I can highlight the angle. Here's your angle, it's up here. So T breaks down, your x component is actually T sine theta. So what does that have to equal, because we're in equilibrium? Well, that will equal the force to the right, which is the magnetic force, which we showed a couple slides ago, which is just ILB, because everybody's perpendicular there, so you just take the magnitudes of each one. The vector cross product works out to this for a magnitude. So you have T sine theta is ILB, then you look in the y direction, T cosine theta equals mg. I wrote it like this on purpose, because whenever you have two equations, one has sine, one has cosine, that's just asking you to divide them. Okay, so you divide those two equations. You've got simultaneous equations. You're allowed to do that. And that gets rid of your tension force, which is good because we're not interested in it at the moment. and you get tan theta is ILB over mg. You solve that for B, plug in all the numbers, and you get the magnetic field is 0.16 Tesla. In another scenario, two parallel wires carrying equal currents in opposite directions repel each other. Find the magnitude of the current in each wire. We have the same free body diagram as part C, but we just have a different magnetic force. So we have two wires parallel to each other, so we're going to use the equation for the magnetic force between two current-carrying wires. And that's this guy right here, and we're finding the magnitude. What do we have? They have the same currents, so I1 equals I2. We'll just replace that with I squared. And the only trick now is a little teeny bit of geometry. We need to know how far apart those wires are. We have theta up here. We have A, the length of the wire. So we know that this piece here is A sine theta. But don't put that in yet, right? Because you also have an A sine theta over here. So it's 2A sine theta. So you plug that in, and here's the magnitude of our magnetic force. From the last page, here's our magnetic force. These are the same equations we used for part C, except we replace the magnetic force with this term here. Once again, we divide them by each other. Sine over cosine turns into tangent. Then we have all this stuff over here. And now we'll go to the next slide to continue the algebra. We have this from the previous slide, and we just go ahead and solve that for I. And that's what we have here. We substitute in all the numbers. And you might have said, hey, here's sine, here's tan. Why didn't you just call tan sine over cosine and simplify it? Well, frankly, that doesn't get us a whole lot. It actually makes it a little trickier, so we'll just leave it in there. Then you go through the calculation, and you get the current is 39 amps.